Hi, this is Chris McCullough at Park. I'm back for another video in this series. This time we're going to talk about double buffered collections, as I promised last time. So apparently I made some minor edit on that, which I don't want. So let's look at Astro Trains. This is where the teaching moment happened to be that I put in here. I'm going to get this out of the way. So we don't need to think about these things, which is why I like being able to hide them. This is why regions are handy, because now code that is several hundred lines away is now much closer. I'm going to hide cleanup here if I can type right. In region typo city. And there we go. Okay, so now this is easier to look back and forth at. So in many cases, I won't do a constant like this. I'll do a read-only string. And so a read-only string would let me do in deep info this.baseinfo.astrotrains tag. In this particular case, the way that it's set up, we have to do astrotrains faction BaseInfo dot astrotrains tag. That's longer to type. Pick your poison. It's up to you. All right. So we've got some lists here, and these lists are what we fill in stage 2. So we're talking about stage 2, and then we're talking about how other things use it. This works for lists. It works for dictionary. It works for Arcen sparse lookup, and it works for single values like a bool or a whatever you have. What do you got? You know, it could be a squad. It could be a anything, any class or structure, anything that would be valid as part of a property. It could be an enum, anything. So that would be double buffered value. In this case, we're looking at lists. So we've got planets with depots, stations, all train guards. These are marked as read-only. The reason why read-only, all that does is say that the list itself can't be rewritten. We don't want the list to be rewritten. The reason we have a name here, and I've got it prefixed and everything, is so that when I do a memory dump, which you can do by hitting, I think, F15, I want to say, you can look and see, well, how many collections of Astro Trains do I have? And if you have more than expected, or you can load up to the main menu, hit F15, go into a game, hit F15, come back out to the main menu, go back into the game again, hit F15, and then do a diff. Then you see if you're leaking memory. So there's a lot of interesting things you can do with that. If you're worried that you have introduced a memory leak, you can find out. Now, I'm also defining how big is the list internally to start with. You may know the base list class in .NET in general starts out at length 16, last I checked. And if you put more than 16 items in, when you put in item 17, it'll double in size. And if I'm remembering correctly, it doubles in size each time. Either that or increases by the original size each time. So it may go up by 16 or it might double each time. I honestly don't remember. So if you know that you're probably going to have as many as, 300 of something. I mean, having an array, a list with an internal array that starts out with length 300 is very, very little RAM. That's just so negligible. We're talking bytes here. Versus 16 versus 300, it's almost nothing. However, if you start with a small list and then it has to keep increasing itself, that is a big hit each time, because it has to make a new list that's the new size, copy over, do an array copy to mem copy over all the stuff from the first list to the second list, dispose of all the stuff from the second list on the garbage collector, from the first list, the original one, and then return the new one. The number one source of cross-threading errors that I actually see are when lists or dictionaries are expanding, because one thread is trying to insert something and another thread is trying to maybe insert something as well, or trying to read, it doesn't matter. But they wind up having a clash because of the internal memcopy stuff that's going on. That's one of the number one places where I see cross-studying exceptions happen. So we're already setting ourselves up for success with lack of cross-studying issues by using these double buffered structures to begin with. But we're setting ourselves up for success in performance by giving them a reasonable starting number to begin, so that they don't have to just keep increasing themselves. And we're reducing the likelihood of cross-studying exceptions if these were to be used less properly than is ideal. So there's a lot to unpack in that statement. Take it from what you will. How the heck do we use these things? Why do we have them? What is a double buffered list? Well, okay, let's talk about graphics. You know about screen flicker and screen tearing that can happen, right? And so there's a lot of different solutions to getting rid of screen tearing that can happen, where essentially you're seeing screen tearing happens when you're seeing part of one frame and part of another frame, because your monitor every pixel isn't updated instantly. It'd be nice if it was, but that's not how, especially in CRT tube days, that's not how that works. And if you're drawing pixel by pixel onto the monitor, then basically it can create a perceptible tear when it's substantially different on one line versus the next. And in the UI, what we usually would see would be a flicker. So you would see, what's the threat right now? The total threat in the galaxy is, it's kind of blinky. It's kind of like 29, 30, it's kind of 29, 30,000 something. I don't know. Why is it all flickery like that? And the reason is that UI thread, which is the main thread of the program, is sampling from something that's being updated on the background, and you're seeing it at different points in the sampling process. So most of the time, it is closer to the real number, which let's say is 30,000, but you could, on one frame or two, see 0. You could see 10,000, 20,000, random numbers. It's just you're kind of watching it add up and fall. And the higher your frame rate is, so in other words, the better your computer is, the more likely you are to actually see that problem. Because if you've got a nice slow computer and you're like, barely getting 30 frames per second anyway, then it's probably closer to being able to be completely calculated and actually close to 30,000 each time. So these flickers in the UI can come from there. But even worse, decision-making flickers, and these are invisible, but they cause weird artificial intelligence artifacts. So essentially, let's say you've got this list of train depots, and you have a function, let's say, that says, I want you to find the best train depot to go kill. And let's say this train depot's list is something you're reading from a background thread, but it's being assembled somewhere else. If we're having that same exact sort of flicker that I just talked about for the UI, then your AI is going to be really, really terrible, because your AI is going to get back not the complete list of train depots. Sometimes it will. And so in that case, when it gets back a list of, let's say there's 30 train depots, I don't know, let's kill the closest one that's the most strategically valuable. And you've got a really great algorithm for figuring out what that is. If you've got all 30, great. It's going to do an awesome job. And you go, I know why it's doing that. If you've got the equivalent of the flicker that I'm talking about, your train's going to do weird things. And you're like, that's not the algorithm I wrote. What the heck? Why is it choosing that train station? Or why is it just sitting there? Or why is it, it's going to vary. And the reason is that when that particular brilliant method you wrote gets called, well, it's got a list of 0 train depots because it happens to be in that particular point of the cycle of filling the train depot list. Or it's got a list of 10 instead of 30, and none of them are in the top 5 that you would want it to actually go for. So it winds up making a really stupid choice because out of the 10 that it was given, it made the best possible choice, but it didn't have all the data, and therefore it made a stupid choice. Those things are incredibly hard to debug. It's incredibly hard to know when it's actually happening, and it leads to all sorts of weird things. It leads to engineers wandering back and forth across a galaxy or across a planet gravity well. It leads to indecisive units in general. It leads to nothing good. And it can also lead to cross-threading errors, where you literally have an exception that is surfaced and interrupts game flow or halts it outright. So how do we solve this? Well, for graphics programming, we have something called a double buffer, right? So the idea is instead of just writing to a naked buffer that is what the human eyeball is seeing right now on the front end, you're writing to a hidden background one that nobody's looking at. And when you're done, you say, I'm done, and you flip it over, and then all at once, that's what the end user sees. Now, obviously, we get into some other stuff with vsync and gsync and stuff like that, but that's still relevant. The double buffering plays into that even so. The same premise comes here. I want my AI and my UI to always be working on a complete list, no matter what. I want to know that the list is full, at least that it's sensible. Now, full, what does that even mean? Okay, so let's say right now we've got 30 train stations, but we just added one more. Does it matter? Do we need to know about that extra one this 10th of a second, or can we wait until, actually this runs every second, so do we need to know about it this second, or can we wait 1 second? Well, the answer to that is where the concurrent list comes in. When the answer is no, we can't wait, then we have to use a concurrent list, and I'll explain that in more detail. But when the answer is sure, yeah, we can wait, as long as we know within, a second or so, if the number of stations that are out there ticks up to 31 1 second late, who cares? That's on human time scale. It doesn't make any difference, and it's probably not going to play into any AI decision making either. It's not noticeable. And now, maybe that sounds like a slack attitude. Who cares? Devil may care attitude. Yeah, let's be slack about things. That's not actually my attitude. The reason I say who cares in that tone is that it costs CPU time to have concurrency. If we're updating this on another thread and we need to know right now, we're going to pay for that in CPU time. So if we need to know, okay, we need to know. We're going to know. And it's going to cost us in CPU time. And so we use a concurrent list, and that's less efficient. How much less efficient? Well, it depends on how many trains you really got in there and exactly how many threads are writing to it. And I mean, it really depends, but it is less efficient. Is it 50% as efficient? Maybe on average. These are pretty efficient to begin with, so it's not the end of the world, but I don't want to throw a lower efficiency tool at everything just because, just in case. You know what I mean? Like, let's use the highest efficiency thing we can. That's how we get to large unit counts, great performance, being able to run on a toaster anyway, all the things that we like, right? And so in the majority of cases, it does not matter if we're up to date 1 second behind. What does matter greatly is if we have an accidental partial list that we're reading from. So we're going to solve that problem. If we need to solve the problem of I need to know now and I also need to never have a partial list, then we have concurrency. So that's the first decision point. So how do we use these? Pretty much the same between the concurrent and the non-concurrent versions. The concurrent version has a few extra features and is missing a few features. The concurrent version cannot sort, for example. So if you're wanting to sort things inside your list, you can't. With the concurrent one, you'd have to read it out into a working list and then sort that. The reason is inherent in the nature of concurrency, and that is a whole philosophical and technical rabbit hole that I don't have time to go down. But so what do? We have two concepts. Now I described the hidden buffer that we're working with that nobody can see, right? And I described the thing that people are seeing that's full. And by full, I mean full of whatever was correct 1 second ago. And it will be correct, full of whatever's correct next when we're done building what we're building. So we have two things, construction and display. The thing we're building, the thing we're showing. And so the first thing we do with all these lists in our stage 2 aggregation, and there is a teaching moment in the code base somewhere or other that actually shows you you can run these on different threads elsewhere too, and then feed them to the main thread or feed them wherever. They don't have to live in this particular thread in this particular class. There are times when you would want to do it a different way, but it's very, very common that you're going to want to do it in the BaseInfo class. So first thing you do, you clear the construction part. This is because we've got a rotating pool, okay? So this is exactly the same as graphics programming. You can see where I got the idea. You don't want to have, what do you do with so okay, we had a complete scene, one frame of a video that we just showed you. And then we took that away and we're showing you a new one that's complete. Cool. What do we do with the one that we just took away? The answer is, it is now the one we're constructing on. The extended answer is, it will be the one that we're constructing on 200 milliseconds to 1 second from now. That's an important distinction because of long-range planning. So we have some long-running threads in this program, and most of them complete in under a couple of seconds. But most of them, when they call something like TrainsEnRoute get display list, they're going to be working with that display list for, a few milliseconds, a second, whatever. Then they're going to lose reference to that particular copy of the list they called, and they're going to call get TrainsEnRoute get display list again, and then use that. We may have swapped out what is the display list in that time. During that time, we need to be careful not to clear something that they're holding on to. So for instance, this gets very technical. The important information to work with this is, do not call clear construction too quickly. You call it at the beginning of your method here, and by this point, anything that was using what is now your construction list as a display list has stopped doing its business. You can be confident of that with the architecture that I have set up for all the threads, with the threading model that we have. You can trust that unless somebody's doing something really weird, in which case we'll deal with that on a case-by-case basis, but in a generalized case, you can trust we're done at this point. We can clear it and we're not going to get a cross-threading exception. Hooray! That's what we want. So we clear, then we start adding to the construction list. None of this is seen by anything. Then when we're done, we hit switch construction to display. This whole process, I don't know, it depends on how long it takes. It could take a few nanoseconds, a few milliseconds in a really bad scenario. It depends on what thread you're on too. Like it doesn't matter. Once it's been switched to display, then you can do a couple of things. You can do display.do4. You can say this dot trains on route. IntelliSense is really slow right now. Dot get display. Come on. Hitting control plus space. That's not it. Silly goose. Get display list. I think it is. Oh, there is no get display list on TrainsEnRoute because this is one of the concurrent ones, and you can't get the internal list because of the needs it has for concurrency. Hold on one second. Okay, sorry. My daughter came home from school, so I paused the recording there for a second. At any rate, we have a couple of different things. This is actually a really complicated example to show you because we actually have nested double buffered lists that are being calculated here. And this is a really useful pattern because trains have guards and we need a double buffered list of that, but we're also double buffering the list of trains to begin with. So first we calculate all the trains, then we switch those to display, then we loop over all the ones that were in our display list, and then we do clears on each of those. And we have an outer all train guards list that we also clear. Then we loop over all our entities, and then we fill using first just the add to construction for the all train list. But then this is an example of how you get the external data on a squad. So at this point, you can have base or deep info on a squad. I have yet to use deep info at all on a squad. There may be some purpose for it at some point, but honestly, I don't really think so. But then again, you guys are creative, so I didn't want to not have that as an option. It uses generics, so you can get exactly what you want by saying get external base info as, and then in brackets say that, and then this is a double buffered list in here. I say add to construction list, and then finally, after we've added all of them in another loop here, then we loop over it again, and we flip that train, and then there's a calculation that we get from there. Do note about this calculation, we're assigning this all at once, or else we would have that same exact double buffering problem. So you can solve a double buffering problem with a variable like an integer, like a total count of strength, by having a like int working strength and then keep adding to the working strength. And at the end, you assign the new strength value to be the working strength, and then it'll never flicker. You can do that, or you can set a double buffered list and then just keep adding to this dot total strength dot construction plus equals blah blah blah, and then finally hit flip and then call this dot total strength dot display when you want to use what the final value is. Really, neither one is more or less efficient than the other when it comes to individual values of that sort. You can see in this particular case, I am not using a double buffered thing. I'm just using the, hey, just assign that when you're done approach. Like assign it all at once, don't assign it as you go. And that's a judgment call. Depends on what you're doing as to what you feel like is appropriate. But, right, so why do we need to have the TrainsEnRoute be concurrent? What does that even mean? Well, concurrent means we can add to the display list whenever from any thread. We won't have a threading exception. Now, why would we want to add to the display list? That's weird. Okay, let's take a look at this. So I'm going to just do a quick search for TrainsEnRoute. This is a quick way to find the deep info, and also in general just to look at what's going on with this. So we can see it exists, we clear it. this clear happens during the cleanup. That clears both lists in the double buffer. And then, we're building it here. Okay, we just looked at all this sort of stuff. All right, no new information so far. Now we're in deep info. This is in the other class. You'll notice in here, we are almost exclusively using display.doFor. We're kind of looping over it and looking at it to do something else. So we're saying display.doFor, hey, look at all the trains. If the train's dead, ignore it, because it'll just get gone the next time. Okay, now get some extra train info. Now we're going to make some decisions. We're going to give some orders. We're going to add some things. This is AI based off of trains, or at least algorithm based on trains. Okay, fine. Over here, we're looping over trains again for some different stuff. Hey, if this train is not got anywhere to go, then maybe give it a place to go, that sort of thing. Here's where we come into concurrency. Nothing so far was a problem. Here's your problem. We, at various points, want to add a train. And when we add the train, in the middle of that same loop, so that same iteration of logic, after we spawn a train, we want to still do some other stuff for all the trains. Now that includes the train we just added. So we've just added, several trains potentially. So then after that, so we've got several trains that we've just spawned here. And then a little bit further down, where did I get? Here. A little bit, sorry. So we added some new trains right here. This code, we're adding some new trains. Down here, for any trains that already existed, plus the ones we just added, we really want to do all of these things. Now, do I personally know that these things absolutely must happen in the way that they do? No, I do not. I have not dissected this code to that extent. Could this wait 1 second? Maybe. I don't know. I don't want to take that chance because this wasn't my code originally. I didn't write this class at all. I just translated it to the new framework. So I'm going to translate it as conservatively as I can, by which I mean as close to the original as I can. If I were designing a new faction from scratch, I would make sure that a 1 second interval is fine, because when I instantiate a train or some other entity, I'm going to attach whatever information it needs to start getting to work immediately. And then if it takes it 1 extra second to actually get to work, that's okay. No biggie. But I don't know that this or any other thing was coded that way. And we can dissect this specific example all day long. It doesn't really matter in the end. From an architectural standpoint, to me, it doesn't matter what the answer is. Sometimes it matters. And so we need to have the double buffered concurrent list in order to handle those cases. I could have spent a while really trying to understand every last piece of everybody's code where concurrency seemed warranted, and see if I can refactor their code to no longer require concurrency. And I did that with Zenith Architrave and Templars, I think, and it was a mess. Partially because I did kind of a half job, because I was, again, trying to change as little as possible. And Zenith Architrave in particular is a humongous monstrosity of a class in all the best ways. It's a really, really cool masterpiece of a faction. The Badger created, and I don't feel like trying to second guess his logic. He wrote it in such a way that it adds a thing when he says it adds it, and he needs to be able to see it in the list afterwards. Okay, I'll make that happen. Here's our double buffered concurrent list. If you have written something similar and you feel like you need that, all right, I trust you. Do it that way. If you are writing something new, consider structuring it in such a way that you don't need to. But if that's going to create harder to read code, code that is awkward, then use the concurrency. You can afford the little extra CPU hit that it's going to take if it keeps your code more readable. That was the second thing, is that even if I were to sit down and spend an extra week refactoring this class and Badger's class and a bunch of other classes to no longer need the equivalent of the concurrent double buffered lists, I don't think the code would be improved. It might run slightly faster for not having the concurrent double buffered list, but very slightly faster, and it would be much, much harder to follow. Right now, I can follow the logic of these factions very straightforwardly because they read from top to bottom in a deterministic fashion, and that's useful. That has tangible value. It makes it easier to maintain, it makes it easier for somebody else to take over, it makes it harder to make a weird accidental mistake. Those are all very tangible values, just as much as saving CPU time has a value. And especially since we're talking about a background thread here in both cases, we really can spare the little extra processing time that the concurrent thread, the concurrent list version adds. So again, we're getting into kind of philosophical territory or design territory or preference territory, but there has to be a balance between code that performs well and code that is readable and easy to maintain. And this is how I achieve that particular balance. So now you hopefully have an understanding of what the double buffered lists do and the concurrent version of them. There are more details about those, and we have double buffered a lot of things. So we have Arcen, double buffered Arcen sparse lookup, and so this is used only for tracing. Looks like here's one that's used for real. This is part of the right. Here's one that's that's tracing only. Here's one that's used for real. So this is part of the new Neinzel sappers coming in DLC 3. So we've got, so this is how many structures are on each planet. Now this is a great example of something that could flicker and cause weird decisions. And I'm pretty sure that actually the code used to do that in a bunch of places, and we just didn't notice most of the time because, again, it kind of corrects for itself. But there's some weird bug reports that are rare that I suspect are actually flickering data in the AI. And I suspect that those bug reports can now be closed. But I can't. We'll give it time and we'll take a look, and there may be more places where we need a double buffer of some sort. So this one does the same sort of thing here. This is going dot construction. So normally, if you've got a sparse lookup or a dictionary, you would expect this sort of nomenclature, right? You are bracketing to say what you're assigning in, like an array, and you're assigning in. That doesn't work anymore with the double buffered version. You have to bracket into the construction one. You can bracket into the display one. Please don't. That's a really bad idea. That's for reading. So elsewhere, you will see we're bracketing into the display one to read. To read? Yeah, sorry. Watched Matilda recently. Yes, to read. And so we are pulling out, so we're reading out of .display, and we're constructing out of .construction. And other than that, it seems exactly like an existing Arcen sparse lookup. It does support sorting. If you are planning to sort a double buffered collection, please do that before you call the switch. So you're going to sort. So for instance, let's take a look at this one. So where's all our stuff here? All right, so we've got a switch construction to display. So before we do that, we could say dot sort. Why is it? Oh, in this particular case, it's construction dot sort. No, it's not. Well, I may not have put the sort method on the Arcen sparse lookups. If you need that, then you can have it. But I'll get back to adding it in. There is a sort on the list. As I said, with the ones that are concurrent, you can't have concurrency and sortedness. That just doesn't work because you don't know what the order is. It's could be any order because there's multiple people adding, right? It is inherently unknowable what the order is going to be inside a concurrent list. So you have to pull it out of a concurrent list first to then be able to sort it. That's the nature of concurrency, is that it is inherently unordered. But still retrievable. So, okay. I'm going to pause here, and we're going to talk about the global world data after this.